Hello, I'm Commander Chris Kreitline, U.S. Navy retired, and I'm going to be giving you a presentation on the Celestial Navigation Triangle. My reference for this is the American Practical Navigator by Bowditch that goes into great detail on the navigation triangle. I'm, of course, going to be giving you an abbreviated version of that. If you ever have trouble getting to sleep at night, you can just open Bowditch and you'll be out like a light pretty soon. Anyway, why would you want to know about the Celestial Navigation Triangle? It's really not critical when you're doing celestial navigation to understand it. You don't really need to do it. You're just looking up stuff in the publications and writing it on the form and coming up with the answer. Well, there are times when you might want to solve the triangle yourself. And I'm going to be explaining those situations in this presentation. Also, if you're crossing the ocean, for example, the Celestial Navigation Triangle can function to give you a course and distance to your destination on a great circle route, which might come in handy. And I'll explain that a little more thoroughly in the presentation. So, sit back, relax, and let's jump into it. Okay, let's talk about the Celestial Navigation Triangle. Once again, I'm Chris Kreitline with Globus Horizon. If you have any questions about this presentation, any corrections, anything wrong you might see in it, please send me an email at sales@globazon.com. I'd be happy to hear from you. Okay, this presentation is really for more experienced celestial navigators, for those that are already familiar with the intercept method with an assumed position. If you're not that far along in celestial navigation, you might have a little trouble following it. But anyway, be my guest. I'm going to be describing the triangle. We're going to be talking about how it's solved and how to use it, how to solve for a line of position in celestial navigation, and also how to solve for course and distance in great circle navigation using the Celestial Navigation Triangle. All right, let's take a look at it. Now, the geometry of the triangle is interesting. It can be all in the northern hemisphere. It can be flipped around. It can be all in the southern hemisphere. It can cross the equator, and in fact, it can stretch around the globe. Don't get hung up on the geometry of the celestial triangle. As long as you enter in the correct entry arguments, you'll get the right answer. I'm just telling you, it can take a lot of different configurations. It is, of course, a spherical triangle. All right, let's take a look at the component parts. First of all, we begin with the elevated pole. Now, this is either the North Pole or the South Pole. It's the one that's closest to the assumed position. Okay, the assumed position is, in fact, the second element of the celestial triangle. The assumed position sits on a meridian of longitude, of course. It has a latitude component. Now we're going to take that latitude component and subtract it from 90 degrees. Of course, there's 90 degrees from the equator up to the elevated pole. So we're going to subtract that latitude from 90 degrees, and it's going to give us this segment of a meridian of longitude. And this is side A of the triangle, and we call it the colatitude side. The next element is the geographic position of the heavenly body you're observing. It, of course, sits on a meridian of longitude also. It has a latitude component that we call declination. Just like with latitude, we're going to take the declination and subtract it from 90 degrees. And that's going to give us a segment of the meridian. That is side B of the triangle, and I call it codeclination. Some books might refer to it as polar distance, but I prefer the term codeclination. Now, the included angle between the colatitude and the codeclination should look familiar to you. It is, of course, the local hour angle from the meridian of the assumed position over to the meridian of the geographic position. Now let's look at an alternate case. This is where the declination of the geographic position is south of the equator, or south or on the opposite side of the equator than the assumed position. Of course, we call that a contrary instance. When you're looking in the site reduction tables, you go to the contrary page in this case. This changes the geometry a little bit of the triangle, and it changes the definition of the codeclination. That becomes then the declination of the geographic position plus 90 degrees. But that's all done for you automatically in the site reduction tables when it solves this triangle. An alternate case number 2 is when the assumed position is west of the geographic position. In this case, the triangle is flipped around, so to speak. Normally, to figure the LHA, you go all the way around the globe because LHA is only measured to the west. Once again, the site reduction tables takes this into account and uses what's called the meridian hour angle, 360 minus the LHA, as the included angle in the celestial triangle. You might have wondered why in the site reduction tables you have LHA on both the right and left sides of the pages. Well, it's to take into account those cases where the assumed position and the geographic position are reversed. 60 degrees on one side is actually the same thing as 300 degrees on the other side. They're complements of each other. That's how the site reduction tables deals with that problem. So what do we have at this point? Well, we've got two sides and an included angle. What we want is the third side, which we call zenith distance, and this other included angle adjacent to the zenith distance, which is angle Z. So these are the component parts of the celestial navigation triangle that we use in celestial navigation. All three sides and the included angles. Now these can be solved with spherical trigonometry. And that's what the site reduction tables do. The tables solve these triangles wherever they may be, anywhere on the face of the earth. The tables are nothing more than lists of solutions of spherical triangles from positions all around the globe. It takes what the navigator enters, the entry arguments of two sides in the included angle, and then it solves for the other side in the adjacent angle Z. It does that hard spherical trigonometry for you. Okay, so we enter in the two sides in the included angle. It solves for the zenith distance and Z. Okay, so when you're working up a site on the site reduction form, you work up three entry arguments: the declination, the AP latitude, and the LHA. And normally you take those three and then you go into the site reduction tables and you extract the computed height, HC, and Z, the azimuth angle. Of course, we take the computed height, we compare it to observed height, and we convert it to an intercept in nautical miles for plotting our line of position. We take Z and we convert it to true azimuth so that we lay out the intercept and the line of position in the right direction. This should all be familiar to you from doing site reduction. But what the tables actually do is solve for the zenith distance. And then they take it and convert it to computed height. But they actually solve for this zenith distance, this third side of the triangle. How do they do it? Well, with this very simple formula here. 90 degrees minus the zenith distance divided by 60. And that equals the computed height. Of course, there are 60 nautical miles in every degree. So it's a simple matter of dividing the zenith distance by 60, and it gives you the number of degrees. Subtract that from 90, and that gives you computed height. I've got a little example right here. If the zenith distance from the AP to the geographic position of the heavenly body is 2,400 miles, we just divide it by 60, and that's 40 degrees. 40 degrees on the arc of a great circle, we know, is 60 nautical miles in each degree. So simply divide 60 into 2,400, gives you 40. Then 90 minus the 40 will give us the computed height of 50. So that's what the site reduction tables do automatically for you. Then you just take it and derive the intercept by comparing the computed height with the observed height. Now the tables also solve for z. And as you remember, the navigator then takes z and converts it to the true azimuth from the AP to the GP of the heavenly body. So that's how the triangle is solved by the site reduction tables. The navigator provides the two sides and the angle, and it derives the third side and the second angle. The third side is converted automatically to computed height. Then we derive the intercept and Zn for plotting the line of position. Well, let's pretend that we're going to forget about the site reduction tables. We want to do it ourselves. Why would we ever do that? Why would we want to solve this navigation triangle by ourselves instead of looking in the site reduction tables? Well, HO 249 Volume 2 that we use as the site reduction tables has limits. It only goes up or down to a declination of 29 degrees. Well, there's a lot of stars that are outside that limit. Stars like Vega, the stars in the Big Dipper, Capella. They're all north of 29 degrees declination. So you cannot use the site reduction tables to solve for those stars. What if your tables are gone? You've dropped them over the side. The dog chewed them up. Well, you don't need the tables. I'm going to show you how you can solve this navigation triangle by yourself. Another reason is just to practice it and to gain a better appreciation for what's going on in celestial navigation. All right, normally to solve this triangle, we go into the site reduction tables with our declination, the LHA, and the latitude. Well, we can do that very same thing with this formula. Now, don't get excited. It's really just add, subtract, multiply, and divide. But we can take the trigonometric functions and solve for the computed height with this formula, just like the site reduction tables do. How do we do it? Well, we're going to use a calculator with trig functions on it. This calculator costs about $14 at Walmart. When you go to get yourself one, make sure you get one that has the trig functions on it so that you can solve the navigation triangle without the site reduction tables. Okay, we can also solve for z with this formula. Once again, don't get excited. It's just standard add, subtract, multiply, and divide. No problem when we use the calculator. It'll give us z that we then convert to true azimuth. Now let me talk about z for just a second, make sure we understand that z, whether it comes from the site reduction tables or whether you solve it yourself with a calculator, is really just an interior angle of a triangle, and it can take a lot of geometric forms. It's not the bearing to the GP of the heavenly body necessarily. You have to be very careful. In this case, for example, it says z is 120. Well, if we tried to plot from AP to the GP for our line of position on a bearing of 120, we're going to be way off. It's going to be way down to the lower right here. So z is just this angle inside the triangle that we always have to convert to Zn. And these are the rules for converting. I'll go over them again in a minute. But we have to convert z to true azimuth from the AP to the GP before we start plotting. Okay, let's look at the form that we're going to use with our calculator to solve the celestial navigation triangle without using the site reduction tables. Well, this form looks very busy, but this is for 3 different stars. It really only has 2 parts. One for deriving the computed height, and the second part for deriving true azimuth. And it looks very busy, but once again, it's just add, subtract, multiply, and divide. You can do it with a calculator very easily. Let's walk through a problem. This is going to be a shot of Vega. Here's the information on it. I worked it up, and of course I knew I was shooting Vega, so it would not be in the site reduction tables. But I worked the form down to the entry arguments for the site reduction tables. But once again, you can work down to these entry arguments on the form, but you're not going to find them in HO249 Volume 2. So in this case, I had to pull out my calculator in the form and do it myself. All right, here it is. All right, we take the declination, put it in here, the latitude of the AP and the LHA. These are the regular 3 entry arguments to go into the site reduction tables. Then we start using our calculator. You put in D and you hit the sign button, and then you write down what the calculator tells you. 0.6266. You write that down. That is the sign of D. Now, one note here. If the declination is contrary to latitude, in other words, if the triangle crosses the equator, one is north, one is south, then every time you enter in the declination of the heavenly body, you've got to label it with a negative sign. Okay, then we continue here. Put in the latitude, hit the sign button, write down what it says. We multiply the sign of D of the declination times the sign of the latitude. Write it down, and it's called the number sign. Then cosine of the declination, the cosine of the latitude, the cosine of the LHA. Once again, you're just punching these into your calculator. Make sure you're writing these down correctly. Don't transpose any numbers or you're going to be making a mistake. Then we multiply the cosine of the declination times the cosine of the latitude times the cosine of the LHA. Put the answer here. Now we're going to take that answer and we're going to add it to the number sign that we came up here. In other words, we're going to add 0.2040 in this example down here to 0.3572. That's what it means here. Add the result of this one to the number that we did up here. The answer is 0.5612. Then you're going to convert it with the inverse sign, once again on your calculator, and it's going to give you the computed height in decimals, 34.14. You should have a button on your calculator that converts that to degrees and minutes, and that will be your computed height. In this case, it was 34 degrees, 8.4 minutes. And that's HC. You're done. There's nothing else. There's no other corrections to be made to it. See, actually quite simple using your calculator. Just don't transpose any of these numbers. All right, now let's move on to ZN. All right, it's essentially the same process. You enter in the HC and push the sign button. Write down the result. Sine of HC times the sine of the latitude. Write it down. Sine of the declination minus the above, and that will be a dollar sign. So this is now called the dollar sign, 0.4439. Then you continue. Cosine of the computed height, the cosine of the latitude times the cosine of the computed height, and that's going to be the ampersand sign, or the and sign, I guess that is, of 0.7826. Then we divide the dollar figure, 0.4439, by the and figure of 0.7826, gives us a result. Then once again we convert it to the inverse of the cosine of 55.44. This is Z in decimals. Well, of course, we're wanting a degree of azimuth, so we're not too concerned about these minutes. We can't plot minutes when we're laying out our azimuth. That's too fine. But we can convert it to degrees on the calculator. 55 degrees, 26 minutes. Well, we discard the minutes. We can't plot minutes when we're drawing a line on a bearing. We'll just take the degree of 55 degrees. Now it's time to see the rules. We come down here to the rules. If you're north of the equator, looking west, then it's 360 minus z equals zn. If you're north of the equator looking east, then it's 360 plus z equals zn. If you're south of the equator looking west, then it's 180 plus z equals zn. If you're south of the equator looking east at the heavenly body, then it's 180 minus z equals zn. So those are the rules. In this case, I was north of the equator and I was looking west at Vega. So I would take 360 minus z. 360 minus 55 is a zn, a true azimuth to Vega's GP of 305. That's what I would use to plot my intercept and my line of position. So that's how it's done. Very easy. That is ZN then. All right, this calculator form for you to use is available for download at globazon.com. And with it, you can derive the computed height and the true azimuth without the site reduction tables. That's the whole point of this presentation, teach you how to do that. All right, now there's another thing you can do, and Bowditch is a good reference on this. You can use your celestial navigation triangle for sailings. In other words, use the triangle to solve for course and distance to a destination on a great circle route. This is not for rum line routing. You don't want to go out for 2 days and go through all this work. Just take your chart out and draw a line if you're taking a rum line. But this is for when you're crossing blue water, when you're crossing an ocean or a great body of water and you want a great circle route, which of course is generally shorter than the rum line route. Well, you can use the triangle to solve for that course and distance to a destination. Let's see how you do that. What we do is we take the triangle and we just make some substitutions. Instead of using the AP, we use our departure point down here. Instead of using the geographic position in the triangle, we use the destination as the GP. In place of the local hour angle, LHA, we're going to use the difference in longitude between the co-declination and the co-latitude of our departure and destination points. And that will give us the zenith distance, as well as Z, which we convert to Zn, which will be our course to destination. So we're going to use the lat long of the departure point, we're going to use the lat long of the arrival point, we're going to use the difference in longitude between the two. All right, it's going to give us the computed height. Well, we're going to convert that back to zenith distance to give ourselves the distance to the destination. It's going to give us Z, and that'll be the course to destination once we convert it to Zn. Let's try one. All right, this is the date. This is one west of Cape Verde Islands heading to Tortola in the BVI. Okay, the declination of the destination here, it was north 18.4167. That's in decimal points. The latitude of the DR position is north 1629, 16 degrees, 29 minutes. For LHA, we're going to use the difference. So we just take the west of one, the west of the other, subtract, and it comes up with 34.68 degrees in decimals. All right, once again, you're always doing it to the west, just like in LHA. All right, we take the form out, we enter in the declination, which of course will be the latitude of the destination. The declination is the latitude of the destination. 18.4167. Latitude of the AP will be the latitude of our DR position, or our departure point. LHA will be the difference of the longitudes. So we've entered those in, then we just start punching it into our calculator. Once again, if your destination is on the other side of the equator, you enter in that part of it, that latitude, with a negative sign. Once again, we just punch it in like we did before. We come on down here. It's going to give us a computed height of 55 in this case, 56 degrees, 55 minutes. Well, what do? We take 90 minus HC, multiply it by 60, just the reverse of what we did before. And that's going to give us how many nautical miles to destination? 1,986. The chart plotter at the time when I was doing this was 1,988, so there was a couple miles difference, not much on those latitudes. But it could be significant if you're going in another direction from different points. So here we figured up the distance. Now let's figure the course. We take the sine of the HC just like we did before. We punch it all in. It comes down to 81 degrees, 25 minutes. We're just worried about the 81 degrees because this is a bearing line. Come down here and look at the rules. If you're north of the equator looking west, then it's 360 minus z equals zn. If you're looking east at your destination, then it's 360 plus z equals your zn. If you're south of the equator looking west, then it's 180 plus z. If you're looking east, then it's 180 minus z equals zn. Well, in this case, I was looking west, north of the equator, so that'd be 360 minus 81 is a course of 279 to Tortola from where we were. All right, the chart plotter, this is ZN, of course. The chart plotter said it was 291 at the time, but that was magnetic. And I was a little confused until I realized it was because the variation of where we were at was very high. And that accounted for that difference between true azimuth and the magnetic bearing towards a destination. Now there's some things I want to remind you of. If the declination and latitude are contrary, then you've got to use a declination sign as negative whenever you put it in to make this work right. If the departure and arrival points are contrary, the arrival point declination sign is always negative. The destination point, if it's on the other side of the equator, you will put it in negative. All right, in conclusion, HO 249 Volume 2 is limited to heavenly bodies up to 29 degrees latitude. Vega Campella, and there's a lot of other very good stars for celestial navigation that are outside of that. So use the calculator. If you happen to shoot those stars, sometime you're out at night and Vega's very bright, you want to shoot it, go ahead. Pull out this form, forget the sight reduction tables, and solve it for Vega with your calculator. You can also use this method, once again, to derive a great circle course and distance to your destination. If you don't have a chart plotter, you might do it, or if your chart plotter breaks, doesn't function, doesn't work, or to double check the accuracy of the chart you're using or your chart plotter, you can use your calculator and the Celestial Navigation Triangle to figure this out for yourself. If you have any questions, I know I went through this pretty quickly, but I'm assuming that you're pretty well experienced with celestial navigation and the intercept method. So a lot of this probably was not new to you at all. But if you have any questions, or if there's anything I said that you think is wrong, please email me at sales@globazon.com. And of course, I want to plug my book, Simple Celestial. If you don't have it, do yourself a favor and go to globazon.com and order it. In this book, I teach celestial navigation, how to shoot the sun at noon for a position fix, and how to shoot all the heavenly bodies in the Nautical Almanac for lines of position using the intercept method with an assumed position. So I hope you enjoyed the video. Once again, if you have any questions, any comments, anything you see is wrong, please send me an email. Thank you.